This talk will explain an approach to software testing based on combinatorial methods and their relationship to software reliability. The goal here is to give you an understanding of why these methods work and how to apply them in practice. And we have a good deal of information and case studies showing that they're very cost effective in reducing errors and at lower cost. My contact information is at the lower part of the screen. Feel free to email me if you have questions or would like more information. And of course, we have downloads of the software and the papers available on our website, which is shown at the end of the talk. Just a quick summary of my background. I have been with the U.S. National Institute of Standards and Technology, also known as NIST, for more than 30 years, and more than 20 years of that has been in applying and researching combinatorial test methods, which I'll be talking about today. Now, NIST is the National Metrology Institute of the United States, metrology being the science of measurement and testing. And so that is why NIST is involved in this work. We seek to develop better methods for measurement and testing and make those available to industry to improve the field overall. So the approach to testing that I'm describing based on combinatorial methods for us began a little over 20 years ago, looking at research on failures in medical device software. Now, we were not looking specifically for combinatorial testing approaches. This was simply research to understand what causes software failures. So this looked at logic errors, input checking failures, errors in calculations, and so on. But one of the things that we looked at were interaction faults. Now, by interaction faults, we mean something like this, which you see in the center of the screen. And in this case, a failure occurs when a particular value is true for the altitude, in this case 0, and volume less than some number. So this is an interaction between two factors. So what that means is that a failure occurs if both of these factors are true, not if either of them. They both have to be true for the failure to occur. So that's what we will call a two-way interaction. And of course, if you test all pairs of values, you should be able to find this fault. And pairwise testing had been used for many years and very effective, but what we discovered was that no one had really looked at interactions beyond two-way prior to this. So we looked at interactions involving 3 factors, 4 factors, and so on. And the result of that is shown in the distribution at the bottom of the screen. So what we found looking at, in this case, 1, 2, and 3-way factors up to 4-way factors, the number of factors involved in a failure is shown on the x-axis. The percentage, cumulative percentage of errors that occur, failures that occur as a result of an interaction with that number of factors is shown on the y-axis. So what this research showed was that about 2/3 of the failures were caused by a single factor, and about 95%, 96% in this case, were caused by a single factor or 2 factors interacting, so two-way interactions. And there were no failures in this data set that involved more than 4 factors. And you can see that if the y-axis reaches 100 with an x-axis value of 4. So that means 4-way interactions, 4 factors interacting. Medical devices are, of course, only one type of software, and there's no reason to assume that the distribution of faults in those devices would be similar in all other fields. So one of the things we wanted to do was to look at other types of applications, and in this case we're showing a graph of the server failures and how they compare with the medical device software failures. So what we see here is what we call the fault profile. This refers to the distribution of interaction faults, or T-way faults, where T refers to the number of factors involved in a failure. The top line in this graph is, of course, the failure profile, fault profile of the medical devices that we looked at in the previous slide. And as you can see here, roughly 2/3 of those failures involved a single factor, again, and 96% involved two factors. However, the lower line is the distribution of faults that we found in looking at open source server software. This is actually a much more complex failure distribution than we have seen for the medical devices. What this shows is that only 40% of the failures involved a single factor, and about 70% involved either one or two factors. So what that means intuitively is that the easy factors have been discovered in the server software, and so the factors that remained after those were discovered were more complex. So in this case, what we can say is that the server software has a better fault profile than the medical devices. Later on in the talk, we'll get to an explanation of why that occurs. We can quantify that and model it, and it does relate to software reliability models, which we'll explain in a little while. Here we're seeing the distribution in red of faults in browser software. This was from one large open source browser. And as you can see, the fault profile is similar to what we have seen for the server. Not exactly the same. In this case, less than 30% of the failures involved a single factor, and a little over 70%, about 75%, involved two factors, and 95% or so involved three factors. But we are starting to see some similarities across these applications. One point is that in this case, and for the server software, 6 factors were involved in a few of the failures, but no more than 6. And we also see that at the lower end with a single factor, relatively few failures involved a single factor, many more involved one or two factors, but getting into 3 or more, relatively few failures involve 3, 4, 5, or 6 factors. The failure profile shown here is a little bit different than the others. In this case, this is in the blue line, the second line from the top that you'll see here. This is initial testing data for a distributed database which was developed by NASA. So the other fault profiles that we've looked at were fielded products or fielded applications, the medical devices, the browser, and the server. But as you'll see, the blue line is actually below the medical device software. So the fault profile for the first time testing of this distributed database is actually better than the fielded products that we saw earlier. Now, that may be due to better testing, better development methods, not clear, but it's an interesting thing to see. This is the fault profile for an SQL database open source application. It's similar, as you can see, to the browser and server software, not quite as good. This may be due to the level of usage and the number of users which would allow the failures to be discovered and corrected. Here we see at the lower line, the light blue line, the fault profile for probably the most heavily used application that we've looked at, the TCP/IP network suite. And as you can see, the fault profile for this is what we would call a better fault profile. In other words, the easy failures involving one or two or three factors have been discovered, and the more complex failures were the ones that remained after those were discovered. Other researchers have looked at the fault distributions for different applications as well, and we've added a few of those into this slide. And as you can see, the number of factors involved in failures is small. So based on what we have looked at and what others have looked at, we can say with a good deal of confidence that the number of factors involved in failures is typically one or two, with relatively few failures involving three or more. And another interesting point is that we have not seen and are not aware of failures involving more than six factors based on the empirical data. So again, the key point here is that the number of factors involved in failures is relatively small, and that has some very significant implications for testing. Here we have the average of the fault profiles shown in the previous slide, and here we can see that 75% roughly were caused by either a single factor or two factors interacting, and more than 90% can be accounted for by no more than three factors. And again, almost all were caused by no more than four factors. Only a small percentage involved five or six-way combinations. So it's natural to wonder what causes this distribution that we've seen in the previous slides. So to understand this, we started looking at the branches that occur in software. In this case, this is a graph from avionics software, so not necessarily representative of all types of software. But this data was from more than 7,000 conditions in if or while statements, in other words, branching statements. And we looked at the number of factors involved in these branching statements, and in this case, a little over 70% were caused by or involved a single factor. More than 90%, around 95%, involved two factors, and so on, as we can see here. And there were a very, very small fraction that involved more than six, I believe less than 1%. If we superimpose the branching statement distribution, in other words, the distribution of conditions in branching statements, with the failure profiles that we saw earlier, then we get this distribution here. And as we can see, the branching statements follow a very similar pattern to the untested or the early test data for the distributed database that we looked at, and also quite similar to the medical device software. And the fault profile is, in a sense, worse than all of the other types of applications that we looked at, the ones that were heavily used. So this gives us a clue as to what may be occurring. So branching statements, of course, are what trigger the paths to different portions of the code. So we can easily see that it would require certain combinations to be true, conditions to be true, to invoke whatever failing part of the code we have tested. So what may be happening is that as the code is heavily tested or heavily used, we basically push the curve down and to the right, in other words, shaking out all of the easy one or two factor faults and arriving at a curve that looks like the ones near the bottom of this distribution. So again, the heavily used applications, the server and browser and TCP/IP and so on, are the ones with the lower fault profiles, the better fault profiles, where the easy failures have been discovered. So this may be what's causing this. And we looked into this some more, and there is a mathematical model that we've developed for this distribution, which we'll talk about in just a little while after we discuss the application of these results. So why does this matter? What is the use of the data that we've seen here? Well, what we can do is consider what conditions are involved in faults, and we arrive at what we've called the interaction rule, which says that when faults are triggered by the interaction of some small number of variables, t or fewer, then if we test all t-way combinations, then we've effectively tested all of the combinations that might matter in triggering a failure. In other words, if all failures involve t or fewer variables, then we would not need to look at higher strength interactions. Now this is what we're calling pseudo-exhaustive because it's not fully exhaustive. However, it does find faults in practical use. As we know, it's almost always impossible to exhaustively test, in other words, to test all possible inputs, but this rule is basically saying that we don't have to do that, although there are, of course, many limitations, so we don't call it fully exhaustive, but the term pseudo-exhaustive expresses the fact that we can test the combinations that really matter. Now, we have looked at validating this rule in real-world software, and an early test of this idea came with the document object model. And this is a chunk of code, about 10,000 lines of code or so, that is found in web browsers. It basically turns the input, the HTML and other input, into images that are seen on the screen. So there is a standard that is used here, and there's another division of NIST that developed conformance tests for this document object model. Now the test covered all possible combinations of discretized inputs, so that resulted in more than 36,000 tests. So that's an enormous number of tests, and it also is a lot of effort to apply these tests because these are image tests, so basically a human needs to compare the results for those 36,000 tests. So that's an enormous problem. So the question came up as to whether we could use the interaction rule, which we have just talked about, to increase the test effectiveness and effectively test all of the combinations that really matter. In other words, could we use the combinatorial testing approach to find all of the faults with less effort? This table summarizes the discretized values, a number of discretized values for the document object model tests. Now, these typically involve continuous values such as location on a screen and so on, so they needed to be discretized, but that of course is a problem with all testing and is used in all types of testing, and there are very well developed methods for doing the equivalence classes category partitioning of the continuous values. So they are discretized values, but putting these values together in an exhaustive form results in more than 36,000 tests, and this is the number of the different factors. So using those discretized values, we did covering arrays that covered the combinations of these values, and the results were very, very useful because what we found was that using four-way combinations, we were able to detect all of the failures that were found using fully exhaustive testing. So this is an important result documenting that the approach is very useful, and in this case, again, less than 5% of the tests that were needed for exhaustive testing were able to detect all of the failures that were involved. So let's look at a simple example to see how this works in practical testing. Now, this is, of course, a selection screen that many of you have probably seen. These are effects for fonts that can be on or off. There are 10 different effects. And so if we have them on or off, then that's 2 to the 10th or 1,024 tests if we wanted to do fully exhaustive testing. But of course, we may not want to do over 1,000 tests. So what we could do instead is look at three-way interactions. As we've seen earlier, in general and on average, three-way combinations account for a very large number, typically more than 90% of the failures. Now, that's not a guarantee that 90% will be found, but in general, it's a practical number. So let's look at how we might do three-way interaction testing for this example. So how many tests would we need if we want to cover all three-way combinations? Well, if we look at 10 variables 3 at a time, then we have 10 choose 3, or 120 interactions of 3 variables, 10 taken 3 at a time. And of course, these are binary values, so that means if we take 3 binary values, then we have 2 to the third, or 8 possible settings, obviously, 0, 0, 0, 0, 0, 1, and so on. So 120 possible combinations of 3 variables and 8 settings for each of these gives a total of 960 combinations. But of course, every test covers many triples, obviously, actually 120 triples, because we have 120 interactions for 10 variables chosen 3 at a time. So we have many triples covered in a single test, but how many tests do we really need if we want to cover all of those 960 combinations? The answer is given by what's known as a covering array, and the number of tests is surprisingly small. Actually, only 13 tests, there is a better array that can be done than this, actually only 12 tests. But a very small number of tests that cover all three-way combinations of these 10 variables. So if we look at this array, each row represents a test. Each column represents one of the 10 variables. So if we take them 3 at a time, we can take them in any order. We can use the ones shown in red, that's 3 columns. Any 3 columns covers all of the three-way settings of these variables, when we can read them left to right, inside out, any way we like. If we look at the first column covered in red, for example, we have 0, 0, 0 in the first line, 0, 0, 1 about halfway down, 0, 1, 0 is the last circled there, and so on. So we've covered all 8 possible settings for every three-way combination of these 10 variables in only 13 tests. So this is a valuable result for testing. This is an extension of the statistical methods developed for design of experiments, originally developed in the 1990s, in this case for the covering arrays. And it's a very hard problem, but there are good practical algorithms that cover nearly all practical applications of testing. So there are good algorithms for almost all the types of testing that you might want to do. Let's look at a larger example. In this case, we have 34 switches that can be either on or off, and let's suppose that we had software that should do something differently depending on the setting of these 34 different switches. So obviously, if we have that many and we start setting them in different ways, then exhaustively we have a very large number of settings. In fact, with 34 switches, then of course we have 2 to the 34th, or roughly 17 billion possible settings of these. So we certainly don't want to do 17 billion tests. So that's really not practical at all, but we could look at doing combinatorial coverage testing of these and take them a few at a time and do still very thorough testing. For example, if we somehow knew that no failure involved more than 3 switch settings, then we could do all three-way interactions in only 33 tests. It might seem surprising, but when you look at the numbers, it does work out. For 4-way combinations, we need 85 tests. For 5- and 6-way combinations, we need a few hundred tests. So that is certainly much better than 17 billion tests. But as we've seen, if we cover, say, 5- or 6-way combinations, then we've effectively covered almost all of the settings that might matter in failures. We've probably covered all of them. So that could be a very effective way to do this testing. So let's try to consider, on average, what this might look like. If we do 3-way combinations, then we have the 33 tests covering something in the average of anywhere from 70, a little over 70%, to nearly 100% of the failures. Again, this is only an average, and we cannot be certain that we will cover something within that range, but another important point of this distribution that we see here is that the the percentage of failures caused by T-way combinations gets tighter and tighter as we increase the interaction strength. So if we go to 85 tests, which cover 4-way combinations, then we get something in a narrower range. On average, we have seen better than 90% up to close to 100% of failures involving no more than 4 settings. So this is a very effective approach, and it works well in practice. Again, it's not guaranteed, but in practice, these are the kinds of results that we can see. Here's another example. We might have configuration settings. These are configurations options from Android smartphone. Different settings, whether the keyboard is hidden or not. Obviously, this is kind of an old configuration where there might be a hard keyboard. But if we combine these, then we have many, many configuration options. And of course, every possible configuration should be something that is processed correctly by the software. So if we start combining these settings, then we could have something that looks like this. Whether the hard keyboard is hidden, yes, no, or undefined. 3 possible settings. Keyboard settings, different types, might be 4. And putting these all together results in a total of nearly 173,000 possible configurations. That's obviously far more than we want to test, so we'll want to do a covering array to take smaller combinations, not trying to do them exhaustively, but covering, say, 3- 4-way combinations of these settings. So if we look at the number of tests required to cover different interaction strengths for 2-way combinations, 3-way combinations, 4-way, 5-way, 6-way, we see the results in this table. There are very small numbers of tests required to cover 5-way combinations. For example, a little over 1% of the exhaustive set covers all 5-way combinations, which is very strong testing. So we can do high-strength testing with a very small fraction of the exhaustive tests. And this, again, is shown to be very practical for real-world testing. So far, we've looked at combinations of many input variables, but we can also use this approach where we only have just 1 or 2 inputs, because what we can do is look at combinations of abstract properties. And this is an example. So this is from the National Vulnerability Database, which NIST maintains that documents all publicly known vulnerabilities in software. And in this case, we had a combination that causes a failure when there are only two inputs, a search string and a replacement string. So the failure says that a single character search string in conjunction with a single character replacement string causes an off by one overflow. So that's a vulnerability. But the key point here is that we have a single character in the search string and a single character in the replacement string. In other words, a two-factor combination. If only one of those conditions was true, then it would not cause this off by one overflow. So what we can do to apply combinatorial testing in a case like this is look at properties of the inputs. Some properties that we could consider for testing are things like string length. There might be 0 characters in one of the input strings, 1 character, something in the middle between 1 and the maximum file length, or it could even be something that exceeds the possible file length size for the system. They may contain embedded quotes, embedded blanks, the file name might be not valid, and so on. So we have a lot of different properties that we could test, and then we can take combinations of these and do a covering array of these combinations. For example, with only 218 tests, we can cover all 4-way combinations of these properties, and that's far less than 2,600 tests that would be required for exhaustive coverage of even this small problem. This is still a small problem, but anytime you want to do exhaustive testing, you need a very, very large number of tests. So this is just another interesting and useful example of the reduction in test suite size. So in general, how many tests are needed? We've seen a number of different examples involving different numbers of parameters and values per parameter and interaction strengths, and this affects the test suite size considerably. In general, the test suite size is proportional to this expression, v to the t log n, where v is the number of values. For example, if it's binary variables, then v is 2, t is the interaction strength, 3-way combinations means t equals 3, 4-way combinations t equals 4, and so on. And n is the number of variables. So the good news out of this expression is that the number of tests increases only with the log of the number of parameters. So even if we have very large test problems involving hundreds of parameters, we can still do them. We've seen examples involving more than 1,000 parameters, and that's still a practical test suite size. The unavoidable bad news, however, is that the interaction strength is t, that is an exponent in this expression, so the number of tests increases exponentially with the interaction strength. Now that's unavoidable. There's no algorithm that will do better than that. It's just the way the math works out. However, the coverage does tend to increase very rapidly, so we have an example below at the bottom of the screen. With 30 Boolean variables, 33 tests will cover all 3-way combinations, but by the time we've gotten to a little over half of that number of tests, we've covered about 95% of these combinations. So this is just one example, but that's the way it tends to shake out in general. So we can still cover a very high proportion of the total number of T-way combinations with a much smaller number of tests than required for the full T-way coverage. And that's because, of course, as we generate tests, we cover combinations as we go along, and towards the end of the array, the number of new combinations tends to grow much more slowly. It just gets harder to find the previously uncovered combinations. So that means that we have this sort of curve in general for most test problems. Reliability models are an important part of software engineering, so we should consider how combinatorial testing fits in with these models. So just a quick review, the interaction rule based on empirical data shows that most failures are caused by a single factor or two factors interacting, and progressively fewer by three or more factors interacting. And also, the empirical data show no failures involving more than six variables, or at least they seem to be extremely rare and are not seen in practice from the data that we have looked at and others have looked at. Now, the reason for this, as mentioned earlier, is most likely, and this seems very intuitive, that the untested applications, such as the database mentioned, that was first-time testing, or applications with smaller user bases. The medical devices, they may have tens of thousands, maybe hundreds of thousands of users. These have simpler faults than the very heavily used applications. The browser, server, and SQL open source software, of course, are used by hundreds of millions of people daily, probably billions in some cases. So the heavily used applications tend to shake out the errors over time, so we would expect the fault profiles for these to be much better because the errors have been removed. The key points do seem to be intuitively obvious. The simpler faults should be much more common than complex faults. This seems natural. And a corollary of that, it should take much longer to find the complex faults. In other words, the faults that involve 4, 5, 6 factors. These should be harder to find than the ones that involve only a single factor. But a key test is whether we can develop a quantitative model that reproduces the empirical data reasonably. So let's start with two assumptions. One, and I would argue that both of these are very natural. The first is that we will assume T-way faults occur in proportion to the T-way conditions in the code, because the code must be exercised in order to reveal the fault. So the T-way combinations must be triggered to lead the execution down that path. The second assumption we'll make is that faults are removed in proportion to the T-way combinations in the test inputs or the inputs of usage, because again we need to reach the conditions that will lead to a fault. So the input combinations are critical in doing this. So let's look at that and see if we can use these assumptions to develop a model that will reproduce the empirical data in a reasonable way. Looking at the distribution of branch conditions for conditions in code, predicates in code for if and while statements, we have the red line, which was shown earlier from more than 7,000 predicates in avionics software. And in addition to that, we looked at more than 400,000 predicates in 6 million lines of code from open source Java applications. So this is basically looking at the distribution of predicates and if and while statements in two different domains. One is very specific avionics, the other are relatively general Java applications. If we look at the table, we'll see that the avionics software, not surprisingly, is more complex. 74% of the conditions in the avionics software involve just a single factor, whereas 88% in the Java applications involved a single factor, and so on. So also note that there were no conditions in the Java code involving more than 6 factors in a predicate. So this is actually quite consistent with the distribution of failures that we saw. Now, if we look at the second assumption that T-way faults are removed in proportion to the T-way combinations of inputs, we can develop a model and look at what will happen over time as these faults are removed. Now let's quantify the parameters of the model. As explained earlier, each set of inputs or each test includes n choose T combinations at each level of T for the n variables or n input parameters. The total number of combination settings, of course, is v to the T times n choose T, as we discussed earlier. So each test or each input set, each set of inputs, covers at most 1 over v to the T of the total number of settings or value combinations. And of course, T plus one-way combinations are covered for each input setting also, or each test. And these will be covered at the rate of 1 over v of the proportion of T-way combinations. So that, again, this is T plus one-way combinations, the next level up, covered at a rate of 1 over v for the coverage of T-way combinations. Now, if we look at single factor faults and we assume that they are removed at some rate r, which we'll designate, for some number of test sets, k, then the proportion that remain, the proportion of faults that remain after k tests or test sets will be 1 minus r to the k. Discovering a particular T-way fault, of course, requires that the combinations in the input exercise or trigger that fault. So a particular T-way combination that triggers a fault must be present in the input. So T plus one-way combinations, as noted, occur at a rate of 1 over v of the T-way combinations. So if we discover the single factor faults at a rate r, then that's going to be reduced by that proportion, or r over v for two-way, r over v squared for three-way, and so on. The minimum value of v, of course, is 2. We're talking about Boolean values. And if we look at just the empirical data, Boolean values tend to be the most common in most software. So we're going to make the simplifying assumption that the proportion of remaining T-way faults after a certain number of test sets k is equal to the expression in the fourth bullet, where 2 is the value of v, because we're assuming that Boolean values are the most common. So if we do that, then we can look at how the distribution evolves as we run more tests or exercise more inputs in practical use. And we'll look at that and see how that compares with the empirical data. So if we start with a distribution of faults that matches the distribution of conditions in code, which is the red line shown on the right-hand graph, and then we will assume that our testing cycle is such that we remove the faults at a rate of 5%, r equals 0.05. K for different values will start from the distribution of the branch conditions, and with testing cycles, the curve moves down and to the right. So this is quite similar to the empirical data that we have seen where the most heavily used applications have the fewest faults of single factors, two factors, and so on. The key test for any model, of course, is whether it matches the empirical data, if it can accurately predict the empirical data. And here we have some really good news, because what we'll show here is that the model actually does predict the data very, very closely. The table shows the actual and predicted values. The graph illustrates those numbers. And as we can see, the t equals 2 through 6 values, which are predicted values, are very close to what the empirical data shows for the average distribution of faults. And the other point that's sort of interesting here is that this is roughly a Pareto distribution with an alpha of 1.5. So what does this model approach mean with respect to testing? Some interesting points. So the first is that it does reproduce the uncertainty and the variability of the distribution of faults. The lower level faults, lower level values of t, single factor, two factor, those have a greater variability because they're found more quickly. And the other really interesting point is that the assumptions that we've made lead to the basic exponential growth model equation that is commonly used. So instead of starting with the assumption that we have an exponential growth model, we start with a little more basic assumptions, and that leads to the standard exponential growth model. And then the last interesting point is that this model also explains why 5- and 6-way faults are very rare in practice, because it's going to take much longer to find them, of course, because the model will predict roughly 16 times the discovery rate for 5-way factors and 32 times the discovery rate for 6-way combinations. So that means that it could take many years to find some of these very complex 6-way faults, for example. To show how combinatorial testing works in practice, we'll do just a quick walkthrough of the ACTS covering array tool that NIST distributes. Now, this is free of charge. We make it available to everyone. There are many other good commercial tools that you may want to consider as well, but this is the one that we make available. Download information is available on the website. So to set up a combinatorial testing project, we simply give it a name, then the parameter name for each parameter one by one, give it the type. You can use Boolean, specify a range of values, or specify individual values, and so on. And then add each one to the table individually, and we end up with something like we see on the right, where the parameters are shown on the left and the parameter values on the right. Again, we need to discretize values, and there are many good approaches for doing this, because that's always a problem in any kind of testing. So if you use category partitioning or some other process to establish these equivalence classes, you can come up with discrete values that are significant for the program. So you do that for each parameter, and then add the system, and then you can generate T-way combinations. One additional consideration is that sometimes you may want to have some subset of the parameters tested to higher strength than others. For example, we may want to do 2-way combinations for everything, but 3-way combinations for some subset. So we're able to do that just by specifying which ones should be selected out for higher strength coverage and specify the coverage level for those. One really important consideration for practical real-world testing are constraints, because almost any application that is used in the real world will have certain constraints that hold true. One of our common examples would be, let's say, if we wanted to test an application that should run on different browsers, different operating systems, and so on. We would not expect to see, for example, Microsoft Edge on a Linux system. So we would want to specify a constraint that says, if the operating system is Linux, then don't generate any combinations that contain Microsoft Edge or Internet Explorer as the browser. And these constraints can be relatively complex. You have typical predicates like you would have in any conditional if statement, while statement, or so on in a program. And you can specify the conditions under which certain values should appear or should not appear. Output can be generated in a number of formats. Most commonly, this will be in a simple spreadsheet table, as you see here, where each row represents a test and each column represents a parameter or input variable, and the entries in the individual cells represent the values for those particular parameters. Output can be in a number of different formats. We could have comma-separated values to make it easy to process through other tools. Also, there might be a need for human-readable output. For example, if we had configurations where we wanted to set up a system for testing, we might want human-readable output that could be used as well. So what I've given here is really just a basic introduction to this approach to testing. There are many good resources to learn and apply combinatorial testing in real-world applications. We have a tutorial that is designed to be concise but thorough enough for use called Practical Combinatorial Testing, and it's available on our website, free download, of course. There are many good videos on YouTube. Just search for pairwise testing, combinatorial testing, and so on. You'll find a lot of good information there, expanding all the time. And there are also many other testing tutorials out there. Just one that I'll mention is the one in the third bullet from Microsoft, very useful and walks through typical examples of this type of testing in practical applications. Here are a couple of good websites for learning combinatorial testing. The first, of course, is ours at NIST. We provide tutorials that I mentioned earlier, large set of technical papers from conferences and journals. All of this is freely downloadable, open source tools. In addition to the covering array tool that we just talked about, there are many other tools that will be covered in later lectures in this course. Also, the Air Force Institute of Technology has a really good website on not only combinatorial testing, but all sorts of good, strong statistical test methods, and that can be found on the link shown here. Just to provide a quick overview of what's available on our NIST website for combinatorial testing, we have downloadable tools, and then we've also tried to break it down into different applications of these methods. So there's a separate section for cybersecurity, of course, that's useful. We also have some new work on autonomous systems and many others. This is the Air Force Institute of Technology website. A lot of good information, tutorials, tools, and also some very interesting and useful case studies that you can find that deal with large complex systems testing. So a quick summary of what we have shown in this tutorial. The first consideration is that the empirical data show that software failures are triggered by a small number of factors, most by a single factor or two factors interacting, and progressively fewer by three or more, and almost always less than 6 or 7 at most. So what that means is that if we cover all t-way combinations for some value of t within the range of 1 to 6, then we have what we call pseudo-exhaustive testing. It's not fully exhaustive, but it's exhaustive with respect to the discretized values of the combinations that matter. So we can do very strong testing with a small number of tests, much smaller than we would require for fully exhaustive testing. And the way to do this is to use covering arrays, which cover t-way combinations. We've shown that there are tools and algorithms that are suitable for nearly all practical problems that we might encounter. And therefore, this type of testing is in practical use today. And there's a lot of good information showing that this does reduce cost and improve test effectiveness significantly. And so it's a useful thing that can be applied today. And we encourage you to get in touch with us if you have any questions. And we'll have information on the website. And of course, again, email if you have any questions at all. Contact information, this is myself and my two colleagues, Raghu Kacker and MS Ronak, email addresses, and the website where you can find the tutorials and papers and download information on the tools.